This video is a follow-on from some of the other non-negative matrix factorization videos. One is like an intro to NMF doing audio decomposition. And then there's another one that talks about seeding the bases and activations. So I encourage you to go watch those first, because what we're going to do here is we're actually going to do NMF in Python, because there are a few things that the Flucoma package doesn't let you do that conceptually feel like we should be able to do. Resynthesizing components using activations and bases that don't match each other. So we could take the activation from the snare drum and the basis from the hi-hat and then combine those together to create a component, create a new sound file that uses those materials to do the resynthesis. Flucoma doesn't let you do that. In Python, we can do that. It doesn't sound as good, and I'll sort of show why that's the case. But I think there's still some potentially interesting sound design features to explore there. So we'll look at how to do that. And then additionally, perhaps in another follow-up video, we will look at doing something like NMF match, but in non-real time. So the NMF match algorithm in Flucoma is very powerful because it lets you seed bases and then essentially match real-time audio against those bases, giving you a real-time activation curve or real-time activation values about how active or present each of those bases are. What NMF match doesn't let you do is do that analysis in non-real time. And the reason why one might want to do this is because it actually lets you do that sort of matching functionality. If I know what spectral templates I'm looking for, I just want to match for those. I don't want to have to do a decomposition or a full NMF on the entire buffer that I want to match those bases against, because that would be computationally very expensive. And so being able to do a sort of NMF match in non-real time with seeded bases will let us look in a very long sound file for very particular spectral templates. And if we can do that in non-real time in Python, this process is a little more automated. It'll be faster. And it'll also be a little easier to do that specific search in a sound file for a spectral template given a seeded basis. That's the goal of these couple of videos. Okay, Python. Here's a Python file, and we're going to need to import Librosa, which is a great tool that, yes, you can see I'm using Copilot here. Librosa, which is a great tool for doing audio analysis in Python. It's really the library for that. We also will need NumPy, and we're also gonna need that, and we're also gonna need that, and we're also gonna need, we might not need that. What we are gonna need is from sklearn.decomposition import NMF. Great. So this will be our non-negative matrix factorization algorithm. We're gonna do that using the sklearn package, and Librosa is how we're gonna get our audio representation, our STFT magnitudes that we're then going to use as our matrix to decompose. Another thing we are going to use is we're going to use argparse to make our function easily callable from the command line. Okay, so the first thing I'm going to do is I'm just going to do an input sound file that we'll use as to decompose. I don't want that to be default, and we will say required is true. And then let's just get the STFT values out of there and plot them, and that'll be our starting point. And then this is going to give us what we're calling Y, which is like our time series from the sound file. This is actually the audio samples, 44,100 of them per second. The sample right here. So let's actually just do a print sample rate. Yep. And then we'll do another one. Yeah, but let's actually print the shape, which I think this should be a NumPy array. So it should be able to give us a shape here. Shape is a method that we would call on a NumPy array. So here's where we'll run the code from, and we'll give it an input. I'm going to actually I'll load in the drum loop from the Flucoma toolkit. It'll be a mono sound file, which will be good. And we know that sound file, so we kind of know what we're looking for. We can know what we're trying to achieve when we hear it. Also, there's a argument in here, mono true. And what this will do, I don't know if it just takes the left channel. I think what it actually does is it'll sum a stereo channel to mono and then give us that information back here. Okay, so I'm going to find that file, which I think I can do by going. All right, so that's going to be the sound file we will decompose. The sample rate is 22,050. Now I know that the sample rate of that sound file is actually 44,100. When Librosa loads a sound file, it by default will load the sample rate at 22,050 hertz. And for most audio analysis tasks, this is going to be just fine. I mean, you're only losing the top octave, and that octave tends to contain less information that is relevant to the type of analysis that people are usually interested in doing. So taking off half of the data in this case is really okay. But because we're going to be using this for creative purposes, I think trying to maintain a high sample rate will be a good thing to do. So if we go here and we say SR equals none, that will actually load the sound file at its native sample rate and give us that sample rate back here. So great. So now we have that sample rate. That's what I want. Okay. So now let's try to plot it. Oh, you know what we have to do first is we have to get the STFT. So let's say STFT equals, that's exactly what I want to do. There, we can set the FFT and the hop length here. And I'm pretty sure for Flucoma, the FFT size and window size default is 1024, which would make the hop length 512. So let's actually put that in here. One thing we might do that could be fun is to actually make those arguments to our script here, which I think maybe I'll do because it'll be a nice thing to do. So I'm going to make both of them not required. And then also, I'm going to change this to 1024. And also, I'm going to do a little check here and say args dot, what is it? Hop length equals args dot hop length or args dot, yeah, this, but not divided by 4. It'll be divided by 2. So it'll default to a half. And we have to make sure it's an integer. And what this will do is it'll say if no value is passed, in fact, what we should do is we should take this off and have no default. So if no value is passed, and so if this is none, then the args.hoplength will default to this, which will be half of our FFT size. The default for FFT size is 1024, so this would default to 512, unless we have a different value for 1024, in which case it'll be, half of that value. Now, another thing we want to do is we want to make sure that our FFT values are powers of 2. So these are the options for our FFT size. I'll probably just leave them at default for the rest of this video, but it's nice to have them in as arguments. So now we have these things here. It'll give us our STFT. And then in order to get the magnitudes, we'll say that we want the absolute value of the STFT because these STFT values are complex numbers. And so if we're taking the absolute value, that's just going to give us the magnitude, the distance from the origin of that complex value of that complex number. And so that will be the magnitude that we'll get. And we can actually get the phases, which we will need later, by taking the angle of that complex number. So that'll give us the phase, which then we can use for our resynthesis later. So now what we want to do is we want to plot the STFT. I mean, we could also plot the audio values. Let's do it. I always have to look up the pyplot or the matplotlib. There we go. Okay. In order for this to line up as it is, you can see now we have the hits actually lined up on the two different plots. We had to tell Librosa.display spec show what the sample rate is. And without that, it was not giving us the right thing. I think it was assuming the sample rate was 22,050 because that's what it tends to default to in Librosa. So it was defaulting to that. But so we have this one has its proper sample rate and this one has its proper sample rate. And now I think it's good. So now what we want to do before we do all this plotting is we're actually going to do the decomposition. And so what we're going to do is we're going to create an NMF model that's going to have, we're going to tell it some number of components that we want it to decompose. We are going to initialize the activations and bases randomly. This is for creating a random seed. And I don't think that we need to worry about that. We're not going to do that. Here, we're actually going to pass in an argument. So that'll be the number of components that we want it to decompose into. And then we'll say W equals model fit transform megs. That's right. Now, the way that this actually works is that once we do the fit transform, this is actually going to give us what we will consider to be the activations. And so I'm translating this into the Flucoma terminology. And so this is actually going to be our activations. And if we go down here, it's going to give us the components. Now in Flucoma, we call the resynthesized buffer channels the components. But in a lot of NMF terminology, the components are actually what we call the bases. And so I'm just going to label them as such here. W and H are terms that are used in a lot of the NMF language. And sort of if you were looking at NMF from a mathematical perspective and computing these matrices and how they're being decomposed and recombined, that's the sort of variables that one would call them. But we're going to use activations and bases here. So let's just try to plot these. $887, that is not right. So this is actually the activations. Oh, you know what? I just remembered that so here's what's happening. So I plotted the bases shape, but it says that it is 3 arrays that are each 887 values long. So I know that that's not the bases because the bases should have 513 or, some power of 2 or power of 2 plus 1 number of FFT magnitudes in them, since that's sort of what they're representing are those special templates. 887 is going to be an activation. And so what we are going to do is we're just going to rename these bases and activations. Now, the reason why these templates or bases are not the components here is because sklearn actually does their NMF with a transposed matrix. You can see this in their help file. Note that the transform data is named W and the components matrix is named H. In NMF literature, the naming convention is usually opposite. So so it's a transposition, it's a matrix transposition error here. If we wanted to, we could transpose our matrix of magnitudes before we do the decomposition, or we could just rename these and that'll be fine. So let's see what that looks like. So that looks great. These look like spectral templates. But you can see now we've totally messed up this guy. And that is because we're saying we want to share X, which we don't want to do. It's going to be a little bit less beautiful of a plot, but I think it'll be obviously better than what we were just looking at. So yes. Now the downside here is that we have a little gap here on either side. And so this doesn't line up perfectly. Like this gap is not represented here. For this plot, if we set the x-axis margins to 0, then we get the white space removed. So now they look nice again. Okay. I'm actually going to leave the white space here because this is not time, right? This is FFT magnitudes, and then this is loudness for our bases. So we'll just leave it as is. Let's plot the activations. And actually, let's plot the activations right here. So all the time-based things are stacked right on top of each other. I think we will have to transpose it. So we'll leave that T there. But what I also want to do is I want to say dot margins X equals 0. Let's see what that does. Yeah, that looks great. So we transpose the activations. And what we can see what that does is if we print the activation shape here, and then also we'll do a print activations transposed shape, activations dot shape. What we can see is the activations shape. This is a 2-dimensional array that has 3 subarrays, and each of those arrays are 887 values long. Those are 887 activation values, 1 per FFT window that gets analyzed across time. But in order to plot it like this on PyPlot, we actually want it to be like this. So we just transpose it into, rather than 3 by 887, we transpose it to be 887 by 3. And then this one is already in this sort of format that is nice for looking at. So we'll transpose it just to look at it there. Cool. So now, yeah, we have our decomposition here. Now, one thing I'll point out is that when I first did this and I listened back to the results that we'll hear in a little bit, I realized that this decomposition is different from the decomposition that Flucoma provides. And the one Flucoma provides sounds better for a few different reasons, which we'll get to later. But the first thing that is better about Flucoma's decomposition is it does a better job of decomposition. So if we just look at the blue and the orange components here, or the blue and the orange activations here, you can see that they're kind of always appearing together. And so that's not as decomposed as we might want it to be. So we're actually going to use a slightly different NMF algorithm here to do the decomposition. And this information came from the Flucoma forum. I went there and asked about this, and Owen Green gave a great answer. He was like, I bet it's this. And then I tried it and it was that. So here's where we're going to put that nugget in. So we're going to use a different beta loss and solver. And this refers to how NMF is actually doing the decomposition, how it's actually driving the activations and bases in the machine learning process. And so we're going to change our beta solver to be the Kullback-Leibler, and we're going to change our solver to be MU, which stands for multiplicative updates. So let's take a look at the results of that. We can already see that now there is better separation. The green, I think here must be the kick. So we have the kick happening in all these spots. The orange is clearly the hi-hat, and we can see that sometimes the kick and the hi-hat happen together, which they do in that sound file. But also they're separate at various points, which is how they are in the sound file as well. And then, of course, here we see the blue as being the snare drum. And so that's where the snare hits are. Okay. So this is the decomposition that we actually want. Great. So now we could use this to recombine the components, recombine the activations and bases into these new components. Let's do our resynthesis right here. So in order to do the resynthesis, we're going to take our activations and bases one by one and combine them back together. Take the activation of the snare drum and the bases of the snare drum and combine them into a matrix of FFT values that we can then use to resynthesize audio. So in order to do that, let's just say for I in range, let's do not this, let's actually do args.endComponents, because that's a little bit more pure of a value to get out of here. What we want to do is we actually want to take the outer product of our activations and bases. This is actually a little redundant, so we can just say that. But what we are saying here is we have this array of arrays that is our bases, and we could actually print and see what that shape is. Yes, thank you, Copilot. Sure, why not? Print that as well. And it'll show us that we have a bases shape of 513 magnitudes for each template, and that's 3 different templates. And then for the activations, we have 3 different activations that each have 887 values in them. So for the activations, we'll just say, yeah, give me the third, give me the index 0, index 1, index 2, and that'll give us a vector of 887 values in each of those cases. For this one, what we're saying, give me all the values, but only if the second array has an index of 0. So it's basically like saying, rather than looking at all 513 groups of 3 values, give me the 0th value for all 513 subarrays. Give me the first value, index 1, for all of the 513 subarrays. Give me index 2 for all the 513 subarrays. And so that's what this is saying. For all of the subarrays, give me just index 0 or index 1 or index 2 of those subarrays. And so this will give us those 2 vectors that then will combine with the outer product, and that'll give us our resynthesized magnitudes. Now, to make sure that we're doing this correctly, I just want to check and make sure that our resynthesized magnitudes are a shape that we think they should be. So it's 513 subarrays, and then each of those has 887 values, which I think makes sense, because what we want is 513 FFT magnitudes going this way, and then 887 values going through time, going that way. So I think this is correct. Now, Copilot was already suggesting this to us, which is that what we want to do next is we want to say that our magnitudes, we need to combine those with phases to create complex numbers, which will be our STFT, that then we can do an inverse STFT on. So the way that we can do that is we can take our resynthesized magnitudes and then combine them with a complex number that is the phases. And here we're turning this into a complex number. This will combine our magnitudes and phases and give us the STFT. And then what we can do is we can say resynthesized component equals, And this will tell us, yes, the inverse STFT with our resynthesized STFT, the hop length should be the same as we had it before. It already knows the window size or the FFT size because it'll be taken from the STFT matrix that we're giving it. So the hop length is important here because we'll determine in the resynthesis how spread out in time each of these resynthesized FFT windows are. So this, I think it really does need to know. Okay, so now we actually should call this Y because that's really what it is. It's actually the time series. So let's call it resynthesized Y. And then what we'll do is we'll actually write it. And I think in order to do that, we need to do a import sound file as SF. That's right. And then we can just do sf.write, and file is going to be the name. So sure, resynthesized, blah, blah, blah. Here's our Y, and it needs to know the sample rate also, right? Because we're writing a sound file here. And so here, the Y here is just a string of samples. We don't know if those samples should be replayed 44,100 of them per second or 48,000 of them per second or whatever. So we need to give the sample rate. So let's see what that does. These will just write into our local folder, which is fine for now. Things seem to have worked. Let's go listen. There's our hi-hat. Now you'll notice it doesn't sound as good as the Flucoma reconstruction. We'll get to that. We'll get to that in a moment. And there's the kick. Just remember that these phases are the same phases as the original sound file, because when we did our STFT here, we actually pulled out the phases into a variable by taking the angle of all the complex values in the STFT. So that is what we're using to do the resynthesis here from our matrix of complex values, which is an STFT, by combining the magnitudes and the phases here to get those complex values. So that's where those phases are coming from.